All right. The last talk for this morning is Andrew Hanlon, who is going to tell us about the Cox category and the homological medicine.
Thank you, and thanks for the opportunity to talk here. So I'm not brave enough to use those whiteboards, so I'm going to try and do everything on my iPad. And if it doesn't work, then thankfully this door is open. I got it. So I'm going to talk about this Cox category that we introduced recently in mirror symmetry, but it'll take a little bit to get there. So, okay, throughout the talk, going to be a smooth projective toric variety. If you want to drop the adjectives smooth and projective, we can in some sense. And if you care about that, we can talk about it afterwards. But I think the story is already interesting in this case. You cannot drop the adjective toric for anything that I say. And okay, so I'll fix a fan for this toric variety sigma in some lattice or in some vector space with a lattice. I mean, you can pretend that this is Rn, but I've been sufficiently toric. It is sufficiently toric so that I write lattices. Okay. So the sort of the goal of this talk and this construction in general is to understand. So we have a lot of wonderful structural results about Raphukaya categories. And okay, maybe this is, you might think this is too simple of a case for it to say anything new, but I claim that some of these structural results tell us new things about the derived category of X, or things related to it. Okay, and I mean, secretly, I won't write this, but then also secretly my agenda is that there are still interesting things that you can say about toric mirror symmetry. Okay, so in order to do anything like that, of course, I need mirror symmetry. So let me state it in the version that I will use. And I guess the first proof in this version, this is always a little bit complicated, but you should probably, like the first real proof, use this machinery of Fong-Lu, Troyman, Zaslow, where you think about do a microlocal sheaf computation instead. But even there, they couldn't quite prove that things generate in the non-equivariant setting, and then there were a bunch of partial results, and then Uegaki did the generals case, and then plus, if I'm going to state it the way that I want, I need this work of Ganatra, Part, and Shenda. And I'll also say, I mean, since I will almost entirely work within the Flora theoretic setting out of preference, you can more explicitly understand this correspondence using work of Muhammad Abu Zaid and his thesis, and then adapted. Like you have to make some small modifications to work in the partially wrapped setting, which Jeff Hicks and I did as some. Okay, so the theorem, after all that like obnoxious amount of writing there, the theorem just says that if I take the derived category or the bounded derived category of coherent sheaves on X, that this is appropriately equivalent to the Raphukaya category of the cotangent bundle of, I take the dual vector space where the fan lives and quotient out by the lattice, or, I mean, for this talk, that's just a real n-dimensional torus, so don't worry too much, and stopped at some combinatorially defined set. Okay, and let me say what this set is. So this F sigma is, well, first I'm going to cheat and tell you what it is in terms of something else that I haven't told you what it is yet. I take this other set L sigma and I intersect the boundary at infinity of this cotangent bundle in the sense of its Liouville structure. And this L sigma is the so-called FLTZ skeleton, where I just take the union over cones in this fan and take sigma cross sigma. Okay, so the sigma, I can identify canonically T star MR mod M with NR cross MR mod M. The sigma perp is in the torus factor, so it's like the orthogonal in the torus to any of the cones, and then the sigmas naturally live in the cotangent fibers of this torus. Okay. So, yeah, so now if I go to GPS and want to try to understand something out of this, well, one thing that I see immediately is that I have natural generators for this Raffukaya category. And okay, maybe these are the less famous natural generators because they're harder to generalize to non-cotangent bundles, but I like cotangent bundles. And the set of generators that I'll take, which are negative. Okay, if I want to be correct, maybe I should say small negative push-offs of cotangent fibers. So I'll write these as L theta. Okay, so let me do an example first. So sort of my running example for this talk, I will take something. Okay. I'll take a Hirzebruch surface of degree 3, and so I'll take the fan, which is generated by, okay, so the standard basis vectors, and then this ray is generated by -1, 3. If I like to draw a picture, maybe this is after FLTZ, I think where these sort of pictures first appeared. Here's my base toric, norma M, and if I draw the projection of this stop F sigma to this set, well, I just have to draw the orthogonals to the rays of this fan. So there's like the two standard basis vectors, and then there's this orthogonal. This thing will wrap around 3 times on the torus, and I can remember the whole stop at infinity by remembering what the normal vectors of these lines actually were. That tells me how to lift up to the cotangent bundle. So I'll draw these so-called hairs on the diagram. Okay, and this one they go in both. But that's only the skeleton. That's only this FLTD stop F sigma for the cones of dimension 1. I had to take the cones of everything, but in this case, the only other cones are top dimensional, so their orthogonal is just this point. And since the fan has full support, I just get like stop cotangent fiber over that point as part of the stop at infinity. Okay, and now I'm saying that a natural set of generators here is just to take the cotangent fibers over every point, right? And the reason why I have to take small negative push-offs is some of them run into the stop, right? So I can take an L theta like here. Okay, so maybe the most canonical one, I can push off negatively from 0. So this would be like one of my generators, L0. And if I was at a point here, maybe I'll also push off so that it doesn't hit the stop. But this one actually equals this. So I don't know, maybe this is slightly off, but this would be like L1/2, 1/6 if I shifted it left a little bit. And this one I can actually isotope to be a genuine cotangent fiber, and the first one I can't. Yes.
We have 2 stops on the vertical line. The y equals x equals 0.
You mean here?
Yeah.
I think I have all the stops that I need. So there are 4 rays to this fan, right? So I drew four hypersurfaces in here. I mean, 2 of them are the same, that bottom horizontal one. I drew the orthogonals to all of them to remember that those one-dimensional rays, cones, and then the only other cones are top dimensional. So their orthogonal is literally the point 0. And then over there, I have every direction. Okay. So now if you if you look, so those generators are rather natural. If you understand mirror symmetry, you might want to ask, like, what do they correspond to, right? So now you can explicitly compute. Well, a couple things. So first, if I want to understand what these generators correspond to, I have to wrap them, because the Floer theoretic functor, or like any of the functors, takes Lagrangians that are wrapped close to the stop, and then I can understand what their mirror objects are. So that these wrap L thetas wrap the sections of the map where I take T star MR mod M and I project to a cotangent fiber. This is the SYZ fibration in this setting. So that tells me that the mirror to these objects are line bundles. And then it's relatively easy to compute like what the underlying function of that gives me the on the base that gives me this line bundle is, and it'll tell me what the Lagrangian section is mirror to. And then I compute that that if I take an L theta, this is mirror to the line bundle on X, or I take the sum over the rays, and I get some formula. So this is the formula to get. I take the floor of minus theta paired with the primitive generator of each ray. I take this linear combination of the generators. Okay, and then if you're me, like 3 years ago or something, or maybe more than that, you look at this and think that's a pretty weird formula, I'll just move on with my life. That's what they are. But if you get more educated, you find this formula appears previously in the literature. So this formula star, which I just mean the right-hand side of this, so at least the first instance that I know of, and here it's really like some slight variation on this, but it's okay, is this work of Thomson, which is just about a purely toric problem, but the line bundles, so what he says is that the line bundles of the form star also have a canonical representation on the B side. So these are all possible summons of so a toric variety has a natural lift of Frobenius to any characteristic. So I can just take the toric automorphism that maps the fan to itself, which on the underlying vector space is multiplication by L. Or in other words, on the dense torus, I just raise all the variables to the power L for some constant. So these are all the summons of what I get when I push forward the structure sheaf under this toric Frobenius map. And really, the more precise statement is that as I vary L, I only get finitely many line bundles. And that if I take a sufficiently large and divisible L, then I'll get all of them at once. But if you want to understand, okay, maybe this is a slight aside from what I want to say, but if you wanted to understand what was happening on this mirror picture up here, as you take L, as you change L, you're just taking the points in this torus that have L, denominator L, and just taking the L thetas at those. So you can see from the picture that if you take L big and divisible, you'll hit every single component of this thing. Okay, and then maybe more relevant to mirror symmetry, you'll see that if you go back like to the origins of this whole FLTZ story, which is this Oberwolfach talk of Bondel, Bondel already had figured this out like a long time ago and proposed that that these were natural generators. So suppose the set, now I'll give it some notation, which you can change, which is capital theta, which is maybe not the best for a board talk, but that's okay. Of all line bundles of the form star are generators of the derived kit. Okay, really, Bondel wrote it over Wolfach note about a talk, and I think had given this talk at various places where he just said that these were generators of the derived category. And then there was some confusion even for a while where you'll find some papers in the toric literature that like assume that that's true, but it was never the proof and never written down. Anyway, so the discussion so far, if I use mirror symmetry though, these guys do generate the category, and we get Vondel's proposal. So the discussion implies the following theorem, which was arrived at independently by Favara Wong, and then myself and Jeff Hicks and Oleg Latsarev. Favara and Wong were more like thinking about, you could do everything in the microlocal sheaf theory of toric mirror symmetry if you want, but they were thinking more in that picture, and these are also natural in that perspective. But anyway, so the Vondel's proposal is true, that these are general. Okay, so that's nice. I mean, you have a nice set of like canonical generators of the derived category of X that are characterized in some way, but you can go even further. You take this geometric story seriously. So, and that's really what Jeff and Oleg and I did in this paper. So here, well, not only do they generate, but if you look at the techniques in partially wrapped Fukaya categories, well, I can understand how, if I pass to the product, how to build the diagonal Lagrangian from these generators. And really what I would do is take a Morse function and perturb the diagonal, and then it looks like a cotangent fiber where it intersects itself, and I just kind of zoom in and take a Liouville truncation. But you can see what happens and explicitly write it down on the other side. So in fact, you have an explicit short, like a minimal length resolution of the diagonal. Or I theta products of elements in this set of line bundles that generalizes Valence's rule. Okay, so for example, maybe because I can't resist, even though it's not the main point of this talk, I can draw a picture of Valence's resolution on the mirror. So you can draw Valence's resolution. Okay, well, I should say that when X is projective space, that this set of line bundles theta are the Valencean collection. It's like O of minus n up to O. And if I take my picture of the torus, so here, if I'm in the mirror to projective space, I have these three rays. This one. This one. Okay, and really, if I'm talking about the diagonal, I'm going to work on the diagonal Lagrangian, which this is also a picture of. But if I make the appropriate sign modifications, then the skeleton on the second factor gets flipped. So I'm going to draw some pairs in the other direction just for my own sanity. Okay, and now let me try and draw a picture of the resolution. So now I'm going to label these by products of line bundles in this collection theta, which I call the Bondel-Thompson collection, which in this case is just the Valencean collection. So here at the origin, I always have the structure sheaf. And on these strata, these one-dimensional strata, I'll have O minus 1 minus 1. So I'm just writing down what you get for L theta if I keep the normal fan, like the typical fan for P2 on the first factor and flip it on the second factor. Okay, so far this flipping didn't matter. And then on these two big strata, I'll have O of, this one will be minus 2 minus 1, I think, with my conventions, and this one will be O minus 1 minus 2. And now the line bundle associated to each stratum, or this cotangent fiber, has natural maps to all the adjacent ones. And so I can just, there are a bunch of maps like this. And like this, that are just given by monomials. And I claim if you collapse this diagram by dimension of the strata, you recover this like unfolded valence and resolution where I've written entirely in terms of line bundles instead of like the valence and tensor the dual. Okay. All right. Well, one thing that's, I mean, maybe not so surprising in this case, but is kind of curious about this Bondel-Thompson collection. So maybe I should have. Because of these two things. Well, for one, if I look at this definition, it only depends on the rays of the fan, not the larger structure of the fan itself. And in fact, this construction, if you do it in the general case, you just draw the same picture and do all the same things, also only depends on the rays of the fan. Like I didn't actually have to, I mean, in this case, not so illuminating, but I didn't have to know that there was more hair at the origin and nowhere else. Okay, so curiously, this construction depends only on the set of rays in the fan and not no higher codimension parts. I mean, I don't know, maybe it's for someone smarter than me, that's not that curious, but at first I was like really worried that we were doing something wrong because of this fact, and eventually I was convinced it was. But okay, so now you think about, well, if you're very torically minded or however you think, or if you like GIT like in the previous talk, then you think, what does sigma 1 tell me? Well, it doesn't tell me about X, right? It tells me about the whole GIT problem that determines X. So sigma 1, so rather than corresponding to X, the set of rays of the fan corresponds to a GIT problem for X. And toric GIT is very well understood. And in fact, I'll think about it as corresponding to a finite set of toric rays. So maybe one of them will be the first one, which I'll call X, and there'll be like up to K of them, which are in bijection with so there are more that I could actually take, but I'm only going to take the chambers of this GKZ fan or the secondary fan. So with the chambers, the GKZ. Okay. And so in particular, since I only take the chambers, like the top dimensional cones, these toric varieties all have fans which are simplicial. Okay, so in my example, or in our running example, so the GKZ fan has two chambers, and it looks misleadingly like part of the fan for H3, but this line is really flat, and the fact that it's in the same dimension is just totally coincident. But anyway, so I have two chambers. One is the chamber this chamber corresponds to my Herzberg surface if I take the quotient, and this chamber corresponds to a weighted projective. Okay, now if you're really paying attention, and I want to talk about derived categories of these things, I really should not think about a finite set of toric varieties, but rather smooth stacks that are associated with those toric varieties. So really, be working with okay. And I want to understand what's happening on the mirror. Well, these things all have the same underlying stratification of the torus induced by the FLTZ skeleton. So, and have mirror skeleton. Stops. Okay, so in my notation, let's call this one x1, this one x2, or maybe curly x2 if I take the stack associated to it. So I already drew this one before, but I'll draw it again just to illustrate the difference. So here's the stop mirror to the Herzberg. So I have this ray, this ray, this ray, all the same. These go here, and then at the origin, I have it. It's the whole. So this would be my F1. Okay, and then the stop for mirror to the weighted projective space is going to look similar. So I'll draw the same exact things. Well, I lose this upward pointing ray in the fan of P113, so it'll be like downward there. I'll have this and this. Okay, and the fan still has full support. So if I was taking the mirror to the variety, this would be the whole thing. But like I said, I really should think about the mirror to the stack, in which case the recipe that I wrote to you is not the right recipe. I have to add something that deals with the fact that I have these stabilizers. And so I pick up at these 2 points a little bit more skeleton. So I have to take the convex hull of these two things that meet here. Okay. So neither of these is contained in the other, but they have the. But if I would have erased all these decorations or hairs that I drew on here, I have the same underlying stratification. And so when I try to like understand how these like L theta Lagrangians and draw some diagram that gives me a resolution, I'm gonna draw the same exact thing, right? Okay, and in fact, I could take an even bigger skeleton. So, and all constructions make sense even on the union.
Yeah, so I think that whenever the toric variety is not smooth, you think of the stack.
Yeah. So from now on, every time maybe this is not the most precise way to say it. When I wrote this warning, I meant like from now on, if you see a simplicial fan that's not smooth, then you take the smooth stack.
Even before the Thompson thing that may not.
Then if it's not if it's simplicial, they might not be line bundles on the thing, but they'll be rank 1 reflexive sheaves. They'll still generate the derived category, but because in fact I can always localize down from the stack to the thing, so it's enough to know it on the stack. But yeah, thanks. So, okay. So the question then, if you look at it this way, and I've presented it in a very leading way, is like, what does this thing correspond to, right? So if I take the union, does it have any sort of algebra geometric meaning? So the first thing that goes wrong if you're like a hardcore believer in the principles of, say, SYZ, is that you can see even in this example, if you do it carefully, that if I look at the SYZ fibers and I look at this stop, the union stop, it's not closed under fiberwise addition. So this Rat-Fukaya category is not monoidal, or not naturally monoidal with respect to the SYZ fibration that's given by projection to the fiber. And so you don't expect this thing necessarily to be a space, but you can do something. So, okay, so before I philosophize too much, let me just give you the construction. So I'll pass back to the B side and just tell you how to build something that's mirror to this. So I'm going to choose. Maybe this is like a definition / proposition. So I'm gonna make some claims, but they're not too crazy. So I'm gonna choose some stack x tilde, which is a smooth toric DM stack with proper birational maps. All of these guys. For all the varieties that I see in the secondary fan, I choose some common refinement. Okay, so this is nothing more than like I have a bunch of simplicial fans and I can always find the common refinement of those, but then I have to be a little bit careful with the stack structure. So I have to maybe add some root stack. Okay. And the fact that these are proper birational maps will imply that the pullbacks on derived categories are fully faithful. But okay, and now I just let. So there's this Cox ring that on ring theory, like that plays the role of the homogeneous ring for projective space for toric varieties and gives you like some algebra that corresponds to all the quotients. So I'm going to let call this the Cox category sitting inside of this be the full subcategory. Let me just say be the subcategory generated by all the pullbacks. Okay. So now there's some claim in here that if I call this a definition, that this doesn't depend on the choice of x tilde, and that's true. So if I picked two different x tilde, I could refine even further and pull back in the category. And you can define. So if I have, it makes sense. Or okay, maybe I should say something more. So okay, so no. If I wanted to actually make the claim that I'm making above, that this is mirror to this thing, you can show that the union of if I take this union skeleton, this is the smallest or the largest, the largest skeleton containing all the Fi. And such that the natural inclusion functors hit these generators. So I'll have functors from these guys into this union, which, okay, maybe you should worry a little bit about in general, but if I'm in the mirror of a smooth projective thing, like I have more naturally I have stop removal functors, and these are the adjoints to them, which exist because everything's smooth and proper. Okay. Hit all the L thetas. Natural generator. So this implies that this union stop category is also, and then that'll sit in any mirrored or refinement, is also like the smallest category that contains all the pullbacks. So this will, if you do this carefully, which I should write up at some point, so this doesn't appear anywhere, but this implies that this is. Okay, so so I told you this construction, and it gives you like a synthesized way, so you can write down these resolutions, the diagonal, like the valence one, you don't get anything new, but like this and these generators, and you have some synthesized way of viewing them in a common category. But okay, if that doesn't tell you anything new, then who cares? So why do this? So the paper that we introduced this in, okay, so I'm gonna apologize to my co-authors, and I'm definitely not gonna write out all their names because somehow we wrote a paper with 9 people. So there's 3 Bs, Ballard, Christine Burkesh, Michael Brown. And this is the hardest part of my so and then Lauren Cranton Heller, so CH is one name. Daniel Ehrman, David Favero, Yoganatra, and then me and Jessica. Okay. Anyway, so this is the paper where we made the construction above should also be credited to this group of people, I guess. So what does this say? Well, this says that you can make sense of theta, and maybe I'll tell you how if I have time at the end, we'll see, in d cox of x, and the important part is the full strong exception. So, in other words, there was this famous and much studied conjecture on derived categories for toric varieties, King's conjecture, which very boldly claimed that every toric variety had a full strong exceptional collection of line bundles, which is not true. The first example was Hilla and Perling, and then Efimov gave it, and then I think McCulloch gave like the first infinite family of examples, and then Efimov gave lots of Fano examples. You can even take PN and blow up at like 2 points. So, or in other words, but if I pass to this bigger category, it's true. So King's conjecture holds for this kind. Okay. Is that a question? And so, and then, okay, maybe more recently, Daniel Ehrman, here I think I can handle it, and myself, and then we recruited a couple combinatorialists because I didn't know that you could, Gaku Liu and Hailun Sheng, I didn't know that you could equivariantly refine simplicial fans commonly, but you can, and it's not actually very hard. You actually, in fact, that theta, you can do this all equivariantly. So theta is if I look at the automorphisms of sigma 1 sitting inside of the automorphisms of the lattice, or if I have any sort of symmetries that preserve one of my GIT quotients, then that group acts on this Cox category, and this is an invariant in the sense that like they're permuted, full strong exceptional equation. Okay, so if I wanted to give this one a phrase, so there's a conjecture of Yurkurev and Panin, which is not false as far as I know. I mean, I don't know if it's true, like it's still open, which says that if I take an arithmetic toric variety and I like pass to the integral closure, then I can find a full exceptional collection that's invariant with respect to the Galois action. And you could ask even like a more general case of this, which I call the geometric Merkurjev-Panin conjecture, and I learned about in this paper of Tevelev and Kastrove, which I just got backwards, but which is you could ask if I have a toric variety with an toric automorphism group, can I find an automorphism invariant full of exceptional collection? And Merkurjev and Panin were interested in the K-theory case, but in any case, if you pass to this nicer category, that conjecture is true in like the most strong sense. So now you have a full strong exceptional collection of invariant line bundles. And in fact, in their original paper, Merkurjev and Panin proved that if I look at, so they actually don't say anything about derived categories. Their thing is all about K-theory. And they prove that the K-theory is not a permutation module of the Galois group, but it's a summand of one. And this implies that, for instance, because K-theory of any of the GIT quotients embeds in the K-theory of the. So the other selfish reason for giving this talk is I wanted to ask the following question, which I think there are many experts in Landau-Ginsburg models here. So if I have a toric, if I look at the individual toric varieties, at least suitably understood, I can find a Landau-Ginsburg model that's mirrored to each of them. But I don't know if I can find one for this guy. So is there a natural? So I did everything just at the skeletal level, but is there a natural LG model here in this Cox scale? Okay. I mean, it looks at, like I said, I can make some intuitive argument that it's not, this guy is not the derived category of some toric stack. I mean, it doesn't have a natural monoidal structure that you would get if it was. But I mean, maybe it still has an LG model mirror that's like not holomorphic or something. And this would be useful for a couple reasons. Well, one, it would be, of course, nice to understand how the story generalizes outside the toric case, maybe to some other GIT problem. Right? And since the construction that I've made was very toric, and even like the mirror picture was very toric, if I knew like some more natural LG representative, maybe it could be helpful. Maybe I shouldn't say would be. It could. The other thing is if I had an LG model, at least like with appropriate properties, I could try to swap the A and B sides. Right, so there's been I think pretty much every, well, I don't know about every, but many of the talks so far, this like behavior of quantum cohomology under refinements of fans, if I restrict to the toric set, has been very important. So I could ask, like, if I can make sense of this construction when I flip A and B, it asks, like, if I take all the GIT quotients together, can I sort of glue their quantum cohomology in some way that makes things even simpler? But that's wild speculation. And the other, like the third reason I might care about this would be that, okay, one natural question you get from this is, okay, King's conjecture is not true, but Kawamata did prove, and then Ballard, Favero, Katsarkov, and Halpern Leisner gave recipes like that show that toric varieties have full exceptional collections, maybe not of blind models, right? But can you get, so you might try to ask, you have this very natural full strong exceptional collection of line bundles on this Cox category, but can you use it to get direct on DX from the Cox? If I understood somehow that this had some like natural LG mirror and maybe these theta things were the thimbles, I could pretend maybe that I could mutate them around until it looked like, till a piece of it looks like D of X, and I just like localize down. That tells me what that piece is. And I mean, if you were even more like pie in the sky, you could maybe try to prove the Mercury-Panin conjecture. If you wanted like something new, but I don't know. So I still have about 15 minutes. So let me just tell you a couple more things. So that's, anyway, that's the question that is on my mind, at least, that I don't know how to approach. But okay, so one thing that I skipped over here is if I was purely on this B side perspective, how do I define these natural generators in this glued category, right? So of course, on the mirror now, I can just say, okay, I'll take these the cotangent fibers at every point. But really the heart of the matter to proving that this is a full strong exceptional collection is making the right definition here. And then you have to do some technique. But it turned out to be harder. Okay, there. Let me tell you how to define this Bondel-Thompson collection on this Cox category. So if I write this line bundle. Another way to think about this, if I like forget about the floor, or if I like unwrap what the floor means, is it's saying that I'm looking at the set of line bundles that are linearly equivalent to something with very small and negative coefficients over Q. So these are like all line bundles that are in the image of like that have coefficients strictly bigger than -1 and less than 0. Okay? So in particular, these are all anti-nav. Or anti-effective, sorry. So this implies, okay, let me write some notation for this. I will call the underlying divisor d theta, because I called the Lagrangian alpha. So this implies that for each theta, minus d theta lies in some cone, in some chamber, let's say gamma I of the GKZ fan. And what I can do is, well, I can define O Cox of d theta. So I'm trying to define like this line bundle in this Cox category to be the pullback from that chamber. Okay, so this category was defined to be the collection of all the pullbacks. And so this will naturally live in the category. So I take O of the stack xi d theta, where minus d theta is there. So in our example, where I start with the Hirzebruch surface, what I would do is take the fan like this, the secondary fan like this, and in this case, there are six of these line bundles. There are 2 like that, and then 4 like that. Sorry, these are the negatives. So these are the negative betas, because now they live in the chambers. And what I would do is, okay, this guy, these guys, I have to pull back from H3. And these guys, I have to pull back from the stack. And then these two, okay, those that live in both chambers, and a little calculation, this is easy, is that if you pull back from either, you get the same length on any common refinement. You can pull back. And then maybe the key, like the hard part, so the calculation that proves that these are full strong exceptional collection is what we call the push-pull lemma, because it's like the push forward of a pullback. There are 8 other authors. I can't take credit for the naming convention. But anyway, so this says that if I take the derived push forward of this Cox line bundle for any of these thetas, and if I pulled it, so which is the pullback of OD theta from some xi, that this is equal to OXJ of any j for all j. And from there, proving that this is a full strong exceptional collection in this category is just like some formal adjoint thing. So now you like look at hom between these two things, you move the push forward over and then you're just doing a calculation on one of the toric varieties, which is easy because you assume that, which has vanishing cohomology because you assume that one of your guys is anti-effective or sorry, is anti-NEF now on that toric variety. And that part's easy. The hard part is proving this lemma, which we couldn't, or at least the algebraic, or there are many of them, algebraic co-authors, collaborators of mine tried very hard to like find some lemma in algebraic geometry about vanishing of cohomology that would prove this, and none of them like quite worked. So we had to like just go into the definition of like a toric cohomology, or really like the picture of how you would compute this push forward on the mirror, and just do the topological argument. Okay, that's all that I want to say. So I don't need to take I have more time, but I think nobody will complain if we have an earlier lunch. So